Hello and welcome to our new series of videos on neurophysiology. Today we are going to talk about neurons, synapses and the action potential. We'll start with the structure of the neuron. We distinguish four basic parts of the neuron: the soma, which is the body of the neuron, the axon, which extends from the soma, the dendrites, the branching extensions of the soma, and the initial segment, the part of the axon where the action potential is initiated. I'm sure you already know these four. However, we can also talk about synaptic knobs or presynaptic terminals, which are the endings of the axons. They are called knobs because of their round or oval shape, which resembles a knob. These presynaptic terminals are very important for synapses because they contain transmitter vesicles with transmitter substances, also called neurotransmitters, that can either excite or inhibit the postsynaptic neuron, the second neuron in the synapse. The presynaptic terminal is separated from the postsynaptic neuron by the so-called synaptic cleft, to which it releases the transmitter substances. Some of the best known transmitter substances you've also probably heard about are, for example, acetylcholine, norepinephrine, epinephrine, or gamma-aminobutyric acid. We'll come back to this in a second, but before we do, we still need to mention some general things first. When we talk about synapses, we distinguish two main types: the chemical synapse and the electrical synapse. In chemical synapse, the first neuron, called the presynaptic neuron, secretes the transmitter substance from its presynaptic terminal, which then binds to a receptor in the membrane of the next neuron, the postsynaptic membrane of the postsynaptic neuron, and excites or inhibits the neuron, as we have already said. This is the usual way of transmitting signals in the central nervous system. In electrical synapse, however, electricity is conducted from one cell to another by protein channels. The presynaptic and postsynaptic neuron are usually connected by gap junctions, a small protein tubular structure that can be found, for example, in cardiac muscle, and which allows movement of ions and other molecules. However, there's not a lot of gap junctions in the central nervous system, so we will only focus on the chemical synapse for now. There is also one important difference in that chemical synapses always transmit signals in one direction only, whereas electrical synapses transmit signals in either direction. Okay, so now let's look at the chemical synapse in detail. We already know what the presynaptic terminal is, but what's also very important is that it has a presynaptic membrane which contains many voltage-gated calcium channels. Now imagine that an action potential has been elicited. This causes the depolarization of the presynaptic membrane, and as a result, calcium channels open and a lot of calcium ions get into the terminal. Because of them, a few transmitter vesicles release their transmitter substances into the synaptic cleft. The postsynaptic neuron has a lot of receptor proteins, and when the transmitter binds to the receptor, it increases the postsynaptic membrane's permeability to sodium. Sodium ions then diffuse inside, and the resting membrane potential becomes less negative because sodium is positively charged. This positive increase is called excitatory postsynaptic potential. In other words, a potential for the postsynaptic neuron to be excited if the potential is high enough. When it does rise high enough, an action potential is initiated, and it begins in the initial segment of the axon because the soma doesn't have enough sodium channels in its membrane, and it is then very difficult to reach the excitatory presynaptic potential. But the initial segment has these much more. The voltage value that indicates that an action potential will be elicited is called threshold. So for example, if the threshold is minus 40 millivolts and the resting membrane potential is minus 65 millivolts, we will need the excitatory presynaptic potential of 15 millivolts. The problem is that an excitation of only one presynaptic terminal wouldn't be enough to excite the neuron, because this when-transmitter substance just doesn't rise the excitatory presynaptic potential high enough. So we need to stimulate many presynaptic terminals at once to reach the threshold. This effect is called summation, because the principle behind it is that the single effects of the presynaptic terminals summate together, work together, so that they can together reach threshold. What can also happen, however, is that there will be a summation, but it will still not be strong enough to reach the threshold, but it will still make reaching the threshold easier. We then say that the postsynaptic neuron is facilitated, because the summation of the presynaptic terminals facilitated the excitation. It made it easier. Now imagine that we want to inhibit the neuron instead. Then there are two options. We can either create the so-called inhibitory postsynaptic potential, or we can inhibit the postsynaptic neuron before the action potential even reaches the synapse. That's called presynaptic inhibition. Let's talk about the inhibitory postsynaptic potential first. What we can do is to open potassium channels, and when the positively charged potassium leaves the cell, the membrane potential will become even more negative. We can also open chloride channels and get negatively charged chloride into the cell. Both potassium and chloride ions hyperpolarize, in other words, make the membrane potential even more negative. And this increased negativity beyond the normal resting potential level is called the inhibitory postsynaptic potential. So we use the excitatory postsynaptic potential when we talk about excitation, and inhibitory postsynaptic potential when we talk about inhibition. The second option, as we said, is presynaptic inhibition, which occurs at the presynaptic terminals before the signal even reaches the synapse. What happens is that an inhibitory substance, usually the gamma-aminobutyric acid, is released onto the presynaptic nerve fibrils before their endings. This causes large numbers of chloride ions to diffuse into the terminal fibril. This again causes hyperpolarization, and the neuron is then less likely to elicit an action potential. The last thing you need to know about is the so-called decremental conduction. To understand it, we need to go back to the structure of the neuron and look at dendrites again. Dendrites can receive signals from other neurons. The problem is, however, that they don't have a lot of voltage-gated sodium channels, and their threshold for excitation is very high. But what they can do is to transmit the electric current in the form of ions down to the soma. But as the dendrites are quite long and have a very thin membrane, which is also partially permeable to potassium and chloride ions, some of these ions will leak out of the membrane, and some of the potential will be therefore lost on the way. So when the potential reaches the soma, a part of the potential is lost. This way of conduction, in which the membrane potential decreases as it spreads from the dendrites to the soma, is called decremental conduction. Okay? So this is it for the first video on neurophysiology. I hope this video helped you to understand how synapses and neurons work and gave you an introduction into the fascinating world of neurophysiology. For more videos on physiology or medicine in general, please subscribe. Thank you again, and until next time, don't forget that medicine can be easy.